Hi everybody, this video corresponds with your participation sheet, sections 2 and 3 for week 7. And title week 7 is Probability and Hypothesis Testing. So I'm going to go through sections 2 and 3 sequentially. And we're going to talk about the answers so you're going to know what they mean. And I'm going to start with, I'm just going to do this pretty orderly. I'm going to talk about number 1 first. In fact, what I'm going to do with number 1 is I'm actually going to, I'm going to get rid of that. It's too thick. And I'm going to actually pare down the size of the, or I'm going to pare down the size of the ink this time. And I'm going to go like this. So number 1. Number 1 is talking about inferential statistics involve predictions based on probability. We already know that, okay? But about what? Probability about what? About the relationship. And what relationship? We're talking about the relationship between two terms, okay? The first term you need to know is this one. Population. I draw a big circle here for a very specific reason. You're going to know about it in a minute. Okay, let's just say that this is a population of anything. Okay, population of could be house cats, could be students at the university. It could be a lot of just any kind of observational unit. Okay, population. Now, what are the odds that the federal government, with all of its largesses and money and time, could possibly research any particular population with respect to any particular characteristic? And the answer is it really can't. It really cannot be done. We cannot. Even with our census, which we gather as much data as we can, okay, we cannot reach each and every individual. So what do we have to do with each and every population we're trying to study? Okay, we're going to have to take a sample. Okay, we're going to have to take a sample. The way I represent this is, as you see right here, okay, I have a population, I have a sample. There it is. There's our sample, there's our population. Okay. Now, with every population, there's going to be some kind of an average. And when we're talking about, let's just make up a scenario. How about this one? Average number of hours of sleep for college students, undergrad college students. And frankly, if we wanted to narrow it down, let's just say Sac State, because if we said all colleges everywhere, wow, that's pretty huge. Let's just say the population of Sac State. Even with Sac State, there is not a great chance that we're going to reach each and every student. Some people aren't going to participate. Some people are not going to give the right information. It's just not going to work out in our favor if we think we're going to get every single person to participate. But nonetheless, hypothetically, there is an average number out there. If we were able to survey each and every student and collect the data, we could find an average. And when we're talking about an average as it relates to a population, we do this. We call it another Greek symbol, okay? Mu. Okay? We're talking about a sample. We're talking about an average in a sample. We already know that character, the X bar. These are important to know. When we're talking about the average as it relates to a population, we use mu. When we're talking about the average as it relates to a sample, we use an X bar. Okay. The only other thing that we need to know for number 1 is that this process of sampling and then inferring information about or some kind of a characteristic about the population based on the sample. Okay, when we do this process, we're participating in a process called generalization. Okay, there we go. There we go. I'm getting faster. Okay, so again, taking a sample from a population, we're inferring from that sample to make some kind of an educated guess about the population. Generalization. Okay, the study is going to take a sample. Any kind of study we do is going to take a sample. Okay, so now we're moving on to what we would call, well, what we're going to do is number 2 here. Okay, I'll read it to you and we'll go through it real quick. Okay, number 2. When we're talking about a characteristic, a studied characteristic of a population, okay, so when we're talking about the population and the characteristics, let's go back to my example. All the college students at Sac State, and what characteristic are we looking for? hours of sleep. The assumption here is that people are sleeping. Okay, that's a characteristic. So it's a variable. It's a non-uniform characteristic of an observational unit. What's the observational unit? College students or Sac State college students. What is the characteristic? It's sleep. When it relates to a population, we call the characteristic, get this, we call it a parameter. Okay. There we go, a parameter. Parameter is a characteristic, and it relates to a population. Okay, it's a characteristic. Okay, for the second part of number 2, when referring to a sample, the same characteristic is no longer called a parameter. It's called a statistic. Don't ask me why. I don't make this stuff up. I'm just telling you what it is. Okay. There we go. Okay, so when I'm talking about a characteristic as it relates to a population, we call it a parameter, and that's easy to remember because P and P, population parameter. And what's this? Oh, this corresponds nicely. Statistic goes to a sample. Okay, statistic and sample. So PP, parameter, population, statistic, sample, SS. So again, those are some easy ways to remember that. Okay, moving over here. I'll just get some more space over here. Okay, number 3 is asking about blank. It's defined by a mathematical equation that shows the proportion or fraction of times that a particular outcome will occur out of all possible outcomes. Well, I know what that is, okay, and you do too now. Okay, probability. There we go. It's supposed to be an A. There we go. Okay, what does this mean, probability? Let me see if I can break this down for you with a picture. Okay, so let's just say we have a die. Okay, it can only be dice if there's more than one. Okay, but we have in this case a die. Okay, just one. I didn't have more than one that day. Okay, there we go. I'm getting there. One more line. Okay, let's just say that we have a die and we are interested in how many times, what's the probability that when I roll this die, it's going to come up as a, let's see, 2. Just make this as clear as possible, 2. So there are 6 sides to a die. So out of 6 possibilities at any one time, out of 6 possible outcomes at any one time, how many ways can a 2 come up? 1. Well, it's the same as all the other numbers on a die, but I just happen to pick on 2 right now. So you got a 1 in 6 chance. And we can leave this as a fraction. We can just say the probability of a 2 being rolled at any roll of a die is 1 in 6. Or if we want to get cute, we can just say, well, 1 divided by 6 is going to give us, okay, it's actually going to be, 0.166666666. Okay, we'll just go like this. Okay. But to make it cleaner, if what we want to do is convert it to a percentage, we're going to just have to multiply whatever the decimal is by 100. And then we have a nice clean percent. So 0.17 times 100. Okay, we're just going to move the decimal over. And we're going to find ourselves with a happy 17%. There you go. That's pretty clean. Okay, so 17%. All right. So that would be, and again, that makes perfect sense because a 1 in 5 would be 20%. And this is a little bit lower. Okay. All right. So now we're looking at number 4. Okay. And for number 4, we're asking a hypothesis considers the relationship between variables in a study. All inferential statistical analyses begin with a blank blank which assumes that no correlation or difference exists between the variables. After performing a statistical analysis, the research will either accept or reject the hypothesis, this hypothesis. Well, this has a specific name. It's called the null hypothesis. We're not going to take anything for granted in science, okay? We say null hypothesis. In a minute, you're going to see a little bit more about what we mean linguistically here. Hypothesis. There we go. Make this S a little nicer. Okay. Okay, a null hypothesis. Let's think about the word null. Okay, nullify, annulment. Hopefully no one here has had to deal with any of that. Okay, nullification. Okay, it means basically nothing or rendered in nothing. Okay, we begin in science with a null hypothesis. The null hypothesis states that we do not accept or find that a relationship exists. It's up to the science or the study that we're doing to, through the data collection and processing statistically of the information or of the data, we're going to learn whether or not we should accept, okay, or reject null hypothesis. Okay, so we get enough, if we get enough information from our data and we apply statistical analysis, we start with the position that there is no relationship between the variables, but once we have done all of our calculations, we may, if we find that it's warranted, we may reject the null hypothesis. Now this sounds a little bit backwards. When you reject the null hypothesis, and the null hypothesis says there's no relationship, by rejecting it, you're saying there is a relationship. So basically, you're getting rid of this. You're basically saying we reject that nothing exists. Doing so, we find that something exists. That's a very confusing thing for students. It's almost backwards. It's counterintuitive when we are rejecting nothing. If you reject nothing, you're finding something. I know, it's a double negative, isn't it? The alternative is, if we don't find enough information to support a relationship existing, then we'll accept the null hypothesis. And if you think about that just slowly, if it says no relationship or there's a null hypothesis and we accept it, then we're accepting that there's no relationship. And again, you're going to hear this enough times it's going to make sense to you. But it is a little bit tricky, at least to begin. So the most important thing about number 4 is to remember that when we begin any study, any kind of inferential statistical analysis, we're going to begin with a null hypothesis. The null hypothesis says basically no, it doesn't exist. No, the null hypothesis assumes that there is no relationship between whatever variables that you are trying to study. I'm going to get us a clean sheet now, and then I'm going to venture into number 5. Okay, everybody, I'm back, and now we have a nice clean sheet for number 5. And the way I'm going to start on number 5 is I'm going to read, in addition, a hypothesis which the researchers believe a significant relationship exists but are unaware to predict the relationship are called blank. By contrast, a hypothesis in which researchers believe a strong relationship exists and they can predict the relationship are known as blank. So the way I'm going to set this up is with something you're already going to recognize, okay? We're going to recognize that it is a normal distribution, okay? Now, if we're talking about variables with a normal distribution, a lot of times we have an x and a y, okay? We have some kind of an independent variable and a dependent variable. We'll talk about that in a while. But nonetheless, what I want you to know right now is that for every normal distribution, we have what we already know, okay, as tails, okay? Kind of perforate this line for a second, okay? Here's a tail, here's a tail. Okay. So when we're talking about tails, okay, we're talking about the values that are at the very ends, okay? If we're talking about values that are low, we tend to be on this side. We're talking about values that are high, we tend to be on this side. Let's just say that we had 2 variables, okay? And they for both for CPS workers. So we got, okay, for CPS workers, we had a population of CPS workers, and we were interested in burnout. And the and we're talking about number of cases for the independent variable. And for the dependent variable, we're going to call this stress level. Okay, stress. So if we were predicting in this study, about which way we expect the relationship to look, we expect that for the high number of cases, okay, so as cases are going up, okay, we also expect stress levels to go up, okay. This is what we would call directional, okay, directional. By contrast, when we don't know which way things are going to go, one way or another, we're going to call it non-directional. So I did that a little bit in reverse, so I'm going to read this back to you. In addition, this is number 5. In addition, a hypothesis in which the researchers believe a significant relationship exists but are unaware to predict the relationship or which direction it's going, okay? Clearly with my example here, we had a direction this way, okay? But when we don't know which way the direction is going, we're going to call that non-directional. I'm going to call it a non-directional hypothesis. Okay. By contrast, when we were looking at that example above, okay, this is actually directional, isn't it? Because we're expecting as cases rise, stress to rise, so they're staying over here. Okay, we're pointing both at the high end of the normal distribution. So we're going to call this directional. Which makes sense. Okay. Must learn to spell faster, right? No, it's all right. We're going to get through it, you guys. There you go, directional. Okay, so whereas this is directional, if we're going to go to either end and we're not really sure which one it is, whether it's this one or it's this one, okay, to help you remember this, we'll go with a question mark. There you go. Okay, so directional, non-directional. Very good. Taking a look at number 6 now. The blank allows researchers to state how likely that an interval contains the population parameters being estimated. Remember when I was talking about the beginning, we take samples in our research. There's no way we can get to the whole population, but we're going to generalize and we're going to make an inference based on our sample and generalize to the larger population. So the blank allows researchers, what I'm about to say, allows researchers to state how likely that an interval contains the population parameters being estimated. This is what you've probably heard before, okay? Confidence interval, confidence, confidence, okay? There you go. Maybe I didn't give you enough room for that on the page. Sorry about that. Another way that the book frames it is called an interval estimate. But because I'm pretty sure you've probably heard the term, even if you didn't know what it meant, even if you didn't know what it meant, confidence interval. That's what we're talking about here. When we have a certain we have a certain level of confidence that the parameter of our population, based on our sample, occurs along the lines of a normal distribution. Okay, that is a confidence interval. Okay, number 7. Okay, the APA holds that the default critical value for a statistical analysis is this. Okay, so the APA, the American Psychological Association, states that basically, if you unless you're going to say one that's smaller, what's accepted as a critical value, which you'll become very familiar in this class with very soon, the default is 0.05, which if you take a look at it, if you were to round, or if you were to multiply that times 100, obviously it's going to be 5%. What this means is this. It means that we're going to allow we're going to allow ourselves 5% error in any study. We're going to get it wrong. The null hypothesis can occur up to 5% of the time, and we're still going to assume that a relationship exists. Okay, that's what this means. So APA says the default critical value, okay, is 0.05. Okay, so fine. Again, I do not expect you to get this right now, but you will. You will. This is your first pass at kind of seeing some of these terms. I'm just putting them out there so that you can see them, but we're going to work with them. But a lot of times, if I just introduce little concepts to you and we work with them a little bit, because you've had some familiarity with them, they tend to kind of build on themselves over time. So again, the APA says that when it comes to hypothesis testing, okay, we're going to assume that we can reject the null hypothesis, okay, even if the null hypothesis occurs up to 5% of the time. So again, if in our research we find that the null hypothesis occurs at 2% of the time, we're pretty comfortable rejecting it. But we can go all the way up to 5% of the time and still feel comfortable rejecting the null. So 5%, okay, or for a critical value of 0.05, okay, yeah, we'll say it's okay to reject null. So I'm going to go to reject. There you go. Okay, okay to reject null up to 5% of the time if it's occurring in your data. Okay, last one, okay, number 8. Okay, when researchers reject a null hypothesis, they should, let me try it again. When researchers reject a null hypothesis that they should have accepted, a blank error has occurred. So let's pretend that we inadvertently rejected a null hypothesis that we should have accepted. So we rejected it, and in rejecting it, we said there was a relationship. Because remember, if it says no relationship and we reject that, we're assuming there is a relationship. But if we do that, we've committed what we call a type 1. Type 1. We'll use Roman numerals. Okay, error. Type 1 error. Okay. By contrast, on the other hand, when a null hypothesis has been accepted and it should have been rejected, guess what we find? Well, what did we do? If the other one was type 1, what do you think this one's going to be? Yeah, you probably figured that out. Okay. Type 2. Okay. There you go. So again, and again, you folks, we're going to go over this so many times. This is your first time even hearing it, okay? First time hearing it. Once you fill in these blanks and you repeat them to yourself a couple more times, they're probably going to make more sense to you. But it's not about perfection right off the bat. It's more about just getting exposure to the concepts, which we'll be using throughout the next few weeks. So again, don't stress about any of this right now. Just make sure that you're writing this down and that you're taking a look at it. From time to time, we'll be reviewing it in class. And now I'm going to go into kind of a fun activity. I think it's fun, about probability. And it's going to involve looking at dice rolls. So we're going to look at that momentarily. Hi, everybody. I'm beginning now, section 3. That's Roman numeral 3 on your participation sheet. You can begin with me by creating a line across. And the way I want you to think about this line is that the lower values are going to go on the left and the higher values are going to go on the right. And I'm going to explain a little bit more about what that means now. I want you to pretend that you have a pair of dice in your hand. And when you roll a pair of dice, or throw a pair of dice, as they say in Reno and Vegas, you're going to produce values. You're going to produce values by the combination of the dice, whatever shows up on top. Now, if you think about it, one die has 6 faces on it. So you've got a 6-face die, and for any number to come up on that die, you have a 1 in 6 chance. Okay, so you got a 1 in 6 chance of rolling any particular number on the die. When you add another die into the mix, you have 2 die, and when you're trying to figure out the total number of outcomes you could have here, you're going to multiply. So when we go across, we're going to go like this. 1 times 1 is 1. Okay, 6 times 6 is 36. Okay, and so we know that you have a total number of 36 possible combinations that you could have for using 2 die. Does that mean that you have a 1 in 36 chance of getting any particular number? No. That's where this whole activity starts. I want to begin with the lowest number you can get by rolling 2 die. If you think about it, you have lowest number you can get on 1 die and the lowest number you can get on a 2nd die. What's that? Well, it ends up being a 2. The lowest number you could get by rolling 2 dice, okay, is a 2. And how does this look in terms of its probability? Well, let's see. In other words, I guess the best way to put it is, what does it look like? I'm going to draw some perforated little lines down here, just kind of makes it easier. The reason I'm doing this is because on the if you're rolling 2 die, okay, you have to be able to see which one comes up in which order, or which one shows up rather on each face. So if we have a pair of die, we actually have 2 slots you could have here. Here's die number 1, here's die number 2. Okay, to get the lowest number you can find or possible, okay, be a 1 on one die and a 1 on the other. So that's the only way you can get a combination to equal 2 when you're rolling a pair of dice. What changes? When we go to a 3, what happens? Let's take a look. I'll do the same setup for you here. It's not glamorous. We're not in this for glamour, I guess. Statistics isn't always sexy, is it? Okay. All right. So we're going to go ahead and come down here, okay, to my 2 columns in each one of these columns. And now, can you think of how many ways you can roll a 3? Or I'm sorry, how many ways can you make a 3 using 2 die? Well, you probably figured this out. Okay. You know that you can go 1 on the first die, 2 on the second. Or, okay, the other way you could look at this, try and make this as nice as possible for you. Okay. You could go the opposite. You could say, well, on our first die, we rolled a 2. And then on the second die, we rolled a 1. Okay, in either space, we have a 3. Okay, so either 1 and 2 or 2 and 1. So you've got 2 ways to make a 3. Okay, so you can see that you can begin to see now, and when we go to 4, it'll make it even clearer for you. You can begin to see how, when it comes to these amounts, not everything's equal here. There is a greater ability to make certain values than others. So as soon as I get to my perforated bottom here, perforated set of columns here, we're going to go ahead and take a look at how many ways you can make a 4. Okay, so how many ways can you make a 4? Well, think about this. You could have a 1, you could have a 3, you could have a 3, and you could have a 1, or you could have a 2, and a 2. Okay. All of these ways make a 4. And there are 3 ways total to make a 4. So you can see as the numbers are getting larger. Okay, we'll do one more together. Okay. And I'll just perforate this first. I guess I don't need to go all the way up, but it just is out of habit for me to do this activity. I've done this activity, it seems like 100 times, but again, I think it makes its point with students. Not that I'm trying to solicit you to gamble or anything like that, but it's just something that it's an easy way to teach probability to students and see the connection between probability and the connection it has with normal distributions. Okay, now we're up to a 5. Okay, how many ways can one make a 5 using 2 die? Okay, well, let's start with I always start with a 1. Okay, then the way that a die shows a 4. It's usually like this. There we go. A little thicker, I guess. Okay, come over here. Okay, there's 4. So on the first example, I rolled a 1, then a 4. Or I could do the opposite. I could roll a 4 and a 1. Okay, alternatively, I could roll to make a 5. Okay, 2 and a 3. Or I can roll a 3 and a 2. There we go. So now we're up to 4 ways you can make a 5 as compared to 3 for a 4, 2 for a 3, and 1 for a 2. So how does this look represented from a fraction standpoint? Well, we have a 1 in 36 chance of rolling a 2. We have a 2 in 36 chance. Okay. I realize you could reduce this a little bit, but nonetheless. Okay, you have a 3 36 chance of rolling a 4. You have a 4 36 chance of rolling a 5. So you can start to see the pattern here. I'm not going to go ahead and do 6 because I'd like you to do that. I'd like you to do 6. As a matter of fact, what I'd like for our class to do is create, just like we did in the first 5 columns with the 2 subcolumns, go all the way over 6, 7, okay, to how far over you think you can get. I want you to notice what happens over time. This is very unique, and I would also like you to tell me what you notice about this activity once you complete it. What did you notice your final outcome is? Because this is going to actually tell us quite a bit about how we understand probability and normal distributions. We spent a lot of time last week and a little bit this week so far on normal distributions. Now we're looking at probability. So once you're done here, what it would be nice for you to have is a completed chart with all of your possible dice rolls plus your percentage, or rather your fractions, along the bottom here of the dice rolls in terms of probability. So we're going to meet or we'll talk about it when we meet and see what you found.